decision tree method for binary exponentiation. Yeah. All right. So for this part, let us use that decision tree model approach, the way to present. How do we organize our data? More specifically, so what is our data? The data is the binary bits. So we derive the bits corresponding to the given integer n, bit sequence. Okay, all right. Then we arrange those bits in a special way. That way is based on the Horner's rule. Horner's rule. Yeah. All right, so let me use the decision tree to do that arrangement. So when we start, a to the nth, so n represented in this special way. Yeah, this way. Yeah. All right, so now looking at this special way, let's do evaluation, based on the bits. How do we do the evaluation? We look at the bits, bit by bit. Yeah. All right, let's start. When we start from the most significant bit, b sub n. Yeah. On our textbook, it uses b sub I, capital I, because this I sometimes could get confused with 1, right? 1, so I replace that capital I by this capital N. Yeah, so we won't get confused. All right. And we also know that b sub n has to be 1. Most significant bit must be 1, cannot be 0, right? If it is 0, then we look at b sub n minus 1 until we get our first non-zero bit. That is our most significant bit. Yeah, so it must be 1. So when b sub n equal to 1, we start from the root node. Then we make the decision, our next decision. We look at b sub n minus 1, 2bn plus b minus 1. Why we do this? Because we get that format from the Horner's rule based representation of n. Okay. So that is important. Where does it come from? From Horner's rule representation. Yeah. So that's the reason. So we look at the b sub n minus 1. There are 2 possibilities, 2 outcomes for our decision tree, 2 branches. The first one, bn minus 1 equals 0. Second one, bn minus 1 equal to 1. Okay? For the 0 case, now we just need to evaluate a squared. Why? Because the bn minus 0, 2bn, that's a squared, right? That's just a squared. Yeah. Square operation. Yeah. All right. For the other case, bn minus 1 equals to 1, this time we need to do a squared times another a cube. So a cube, see, a cube, a squared, a cube. Okay, all right. So that's the 1 step forward, right? 1 step forward. Next, we want to go to the general step, right? Yeah, because we cannot do this way many, many times. So here, let me describe the general way, all right? When we go down to the next level, yeah, we represent our current situation, a to the p. Yeah. So p could be 2 or p could be 3. Okay? Yeah, the current p. So this is the current p. Current p. Okay? So that's our starting point. Current step, starting point. All right. Suppose we start with a to the pth power. Okay? Yeah. Then when we go to the next level, all right, so suppose we want to evaluate a to the 2p plus b sub little I, b sub I little I, okay? Still based on the Horner's rule. Yeah. Two possibilities for b sub I. The first one, bi equals 0. Second one, bi equal to 1. Yeah. But for the first case, we do the square operation on a to the pth power. Square it. Yeah. For the second possibility, a to the pth, the whole term, we assume we have the value already. So we square it, then do another multiplication. Dot a. Yeah. Two cases. See? Yeah. Keep doing this pattern again and again until we reach the last bit, B0. Okay? Yeah. So at the end, let me do the summary. Now, following this procedure, we can write our code. Yeah. To write our code, so let's do this way. So we have a for loop, yeah, because the number of bits is known, right? The number of bits known here, so we can create a for loop. Iteration by iteration, okay? When we start, we set initial value, p equals 1, right? Corresponds to the bm, bm equal to 1, yeah, that's our initial p. Then at that time, I equals n minus 1, because the first bi we need to use to tell us which branch to go. So that's the bn minus 1. Yeah. After that, then we do calculation operation. So what kind of operation? A to the 2p plus bi, all right? And we know how to do it, you know, double, right? Then look at the bi value. Do we need another multiplication or not? Okay, so we can do that easily, right? All right. Then update. After that, before we get to the next iteration, we need to update some variables. The first one, p, we need to update 2p plus bi. That's our new current p. Yeah. Then I, we need to update. Yeah, that's actually the counting variable reduced by 1. Counting variable reduced by 1. All right. Yeah. Then iteration, the same pattern another time. Yeah, until we reach the end and get out of the for loop or while loop, you know, some loop. Yeah, you choose, you like to choose. Yeah. So that's the whole procedure. I think based on this diagram, decision tree structure, you can easily write the program. Even we convert it to the matrix multiplication, you can write your program in the similar way, right? Yeah. All right. So that's the, you know, the algorithm detail part. So that's our algorithm detail implementation part. Okay. All right. But we have not completed this topic yet. We have our last video. I want to show you several examples to give you better view, better picture, better understanding for this algorithm. All right, so let me stop it right here first.